notice in the next few videos, we will learn about the formulae you are required to know for CXC CSEC physics examinations. These formulae are required under the CXC 2015 CSEC physics syllabus. Such syllabus normally runs for 10 years, after which they are revised and updated. In terms of formulae, a revised syllabus will not have much change since these formulae are based mainly on classical Newtonian physics. Formulae you are required to know for CSEC physics examinations. We begin with section A, mechanics. This section has the most formulae, 17, when compared with the other 4 sections. There are some basic principles that we need to learn to apply to all 35 or so formulae. First of all, we have to remember what the formulae are. You will not be given a table or a sheet with physics formulae for this exam, unlike math. You have to know the formulae, which represents the variables, including upper and lowercase letters. Secondly, you need to remember what the symbols represent and the required units allowed in that formula. Thirdly, if required, you need to change the subject of the formula. Fourth, substitute the given values in the formula and solve. And fifth, check that you have the correct number of significant figures and the correct unit for the answer. Lastly, subjectively evaluate your answer by asking yourself, is my answer reasonable? For example, if you have to find the average, the mean of 12, 15, and 20, and you get 21 or 11, you know that these are wrong since the mean must be greater than the least number and it must be smaller than the greatest number. Now for section A, mechanics, these are the formulae that we need to learn. CXC does not require you to know or to memorize these two. You do need to know how to use them though for math. But if you know them, and we will learn them, then another component, another aspect of this physics syllabus becomes easier. For thermal physics, these are the formulae that you need to know. For wave, which deals with sound and light, you have these 5 formulae. For electricity and magnetism, we have these formulae listed here. Really, we have 7 formulae since this last one is actually a combination of those 2. And for atomic physics, there are a few formulae, including atomic number, and also we need to deal with some half-life decay calculations. So let's get back to mechanics. In this video, we will consider these 6 formulae from section A. That one, F is equal to ma. This one, P is equal to mv. This one, T is equal to F times perpendicular distance. Number 12, W is equal to F times D. Number 16, W, which is something different from that W up there, is equal to mg. And number 17, E is equal to mc squared. We are considering these 6 formulae because they are fairly simple, since they all have a format that you have learned in grade 3 or 4 when you learned area is equal to length times width. That is, one quantity is equal to the product of the two other quantities. In this case here, we are dealing with the area of a rectangle. You have learned that in grade 3 or 4, and these 6 formulae that we will be looking at, they all follow this same format here, where one quantity is equal to the product of two other quantities. So let's begin with F is equal to ma. Now in this formula, F stands for force and it is measured in newtons. M is for mass and it must be in kilograms. And A is for acceleration, which must be in meters per second squared. First example, a body of mass 20 kilogram experiences an acceleration of 5 meters per second squared. What is the net force acting on the body? Well, first of all, we'll write the data that we are given. We know what the mass is. We know what the acceleration is. We want to find the net force. The formula relating these three things that we know is F is equal to ma. So we will substitute M and A, and we get the net force F is equal to 100 plus or minus 50 newtons. Since we have one significant figure here and one here, our answer can only have one significant figure, which is that one. So if we write 100 and leave it like that, CXC will accept it. But it is better to write 100 plus or minus 50 newtons, which signifies that you are rounding off at this hundredths position. Or you could say 100 newtons correct to one significant figure. That's one example using that formula. We look at another example. A body has a mass of 20 kilograms and experiences a net force of 200 newtons. What is its acceleration? Well, now we know the mass and we know the net force. We are asked to find acceleration. We have a formula relating these three variables here, which is F is equal to ma. We need to change the subject of the formula. So A is equal to F over m, and then we substitute F and m, and we will get an acceleration of 10 meters per second squared. Again, we are dealing with one significant figure, so our answer can only have one significant figure. We are rounding off at this tens position, so our margin of error will be 10, which is 5 more to 5 less. Or you can say 10 meters per second squared correct to one significant figure. Now we take a third example with F is equal to ma. A body of mass 400 grams experiences a net force of 200 newtons. What is its acceleration? Now this time the mass is given in grams, and we know that mass can only be in kilograms here. So we need to carry that 400 grams to kilograms. The force is in the right unit. We want to find acceleration. If F is equal to ma, then A is equal to F over m. We substitute F and m, and we get 500. Again, we are rounding off to one significant figure. So we are rounding off at this hundredths position. Half of the hundredths position will be 50. So our margin of error will be 50 more to 50 less. Now we look at this other formula here. P is equal to mv. In this case, P is momentum, m is mass in kilograms, v is velocity in meters per second, Now, what do we mean by momentum? Momentum, P, is defined as the product of the mass and the velocity of a body. As you could see, P is equal to M times V. A body of mass 20 kilograms has a velocity of 3 meters per second. What is its momentum? So we know the mass, we know the velocity. We want to find the momentum. Do we have a formula relating these three variables? Yes, P is equal to mv. We want to find P. We know M and we know V. We substitute those in the equation and we get 60 kilogram meters per second. Again, we are rounding off. We have one significant figure there, one significant figure there. We are rounding off our answer to one significant figure. So we are rounding off at that 6, which is in the tens position. So our margin of error will be 5 more to 5 less. We can also say 60 kilograms meters per second correct to one significant figure. Let's look at another example using that same formula. A body of mass 800 grams has a momentum of 500 kilograms meters per second. What is its velocity? So we know the mass and it must be in kilograms. Even though we are given it in grams, we must carry it to kilograms by dividing by 1,000. We know the momentum. We want to find the velocity. Do we have a formula relating those three variables? Yes, P is equal to mv. We want to make V the subject of the formula. So V is equal to P over M. You substitute those values, 5,000 kilograms meters per second, divide by 0.8 kilograms, and we get this 6,250 meters per second. However, remember we are dealing with significant figures. This is one significant figure. Mass is one significant figure. Momentum is one significant figure. So our answer can only have one significant figure, which is that 6. We will have to round off at that 6. So we drop those and add zeros to make up the space, and we get 6,000. But since we are rounding off at the 6,000, margin of error is 1,000, which is 500 more to 500 less. So our answer is 6,000 plus or minus 500 meters per second. We said that momentum is defined as the product of the mass and the velocity of a body. There is a derived formula using P is equal to mv, and that makes use of the principle of conservation of linear momentum, which states that if two objects collide, then the total momentum before and after collision will be the same if there is no external force acting on the colliding objects. Which means that if m1v1 is the momentum of one body and m2v2 is the momentum of the other body before collision, and then the two body combines as one, then m3v3 will be the final momentum. A trolley of mass 6.0 kilogram traveling at a speed of 4.0 meters per second due east comes in non-elastic impact with another trolley of mass 8.0 kilogram traveling at 3.0 meters per second, also traveling due east. If the two trolleys combine and continue to travel as one body, what is their final velocity? We have to state magnitude and direction. So we flip that formula around and we say that m3v3, which is the final momentum, of the two bodies together is equal to M1V1 plus M2V2. If we let the ones represent the first trolley, and the twos represent the second trolley, and the threes represent the fused or joined trolleys, then what we have is M1 and V1. We have M2 and V2, we know those. We have M3, which would be the combined mass, and we want to find V3. So we use this formula that we had up there. We know that, we know these, we know these. V3 is equal to M1V1 plus M2V2 together, divide by M3. We substitute our values in there, and we come up with 3.4 meters per second due east. The two trolleys were traveling east. Since we are rounding off, we have two significant figures, 2, 2, 2, and 3. Our answer can have up to two significant figures, which would be 3.4. And since the 4 is our uncertain digit, then our margin of error is half more and half less of that position, which is 0.05. So 3.4 meters per second correct to two significant figure due east. Now, what if they were traveling in exactly opposite direction? One trolley was traveling going east, and the next one was going west. East, west. Then we will assign one direction or velocity or momentum positive and the other negative. So P1, let us say this here is P1. That will be 24, positive 24. And this one here going west, okay, that one was going east. This one going west will be negative 24 when we multiply 8 by 3. So that V3 will be 24 plus negative 24 divided by the total mass, and we get 0. Now in this case, the two trolleys are going in opposite direction, and the momentum will not cancel out one another. A trolley of mass 9.0 kilogram traveling at a speed of 4 meters per second due east comes in non-elastic impact with another trolley 8.0 traveling at 3.0 meters per second traveling due west. If the two trolleys combine and continue to travel as one body after impact, what is their final velocity, state magnitude, and direction? So we will let the ones represent the first trolley, and the twos represent the second trolley, and the threes represent the combined or fused trolleys. So when bodies travel in exactly opposite directions, as in this case, we assign one direction or momentum positive and the other negative. In this case, we will assign west as negative. That trolley, the ones, is traveling east. Its velocity is positive. The other trolley is traveling west. Its direction is negative. And this is the combined mass of the trolleys. We want to find the velocity and the direction after impact. So M3V3 is equal to M1V1 plus M2V2. We substitute the numbers we have up here, and we find that we ended up with 0.70588, which we will round off to two significant figures. But since we are rounding off at this position, we take half of that position, which is 0.005, as our margin of error. And since our answer is positive here, and we assign east the positive direction, then the trolleys will end up traveling due east. The final direction corresponds with the sign of your answer. Positive in this case is east, negative is west. Our answer here is positive, so it is traveling east. The moment of a force, we are not talking about momentum, we are talking about moment. The moment of a force, and the symbol for that is an uppercase T, is the product of the force and its perpendicular distance from the pivot or the fulcrum, and that makes use of equation 8, which is T is equal to F times perpendicular distance. If you have a spanner like what we see here, and a mechanic is applying a force here of 264 newtons at a distance of 0.35 meter to attempt to tighten that bolt, then the moment of the force is the force itself times the perpendicular distance. The force is 264 newtons, the perpendicular distance is 0.35 meters. What is the moment? What is the turning force? The moment will be the force times the perpendicular distance, and so in this case we get 92.4, but since this is the limiting factor in terms of significant figures, we can only have two significant figures, 9 and 2. We drop that 4 and we get 92 Newton meters. Our uncertain digit is this 2, which is in the ones position. We take half of that position more to half less. So we get plus or minus 0.5 Newton meters. Let's look at another example of moments. Similar to the one we just looked at, a mechanic applies a force of 45 newtons on a spanner at a perpendicular distance of 0.65 meter from the pivot or the turning point. Calculate the moments, which is sometimes called the torque, the turning effect of the force. Well, we know what the force is, we know what the perpendicular distance is. We want to find moments. We do have a formula with these variables, and it is T is equal to F times perpendicular distance. We substitute F and perpendicular distance, and we get 29.25 Newton meters. But remember, we have to look at significant figures. This has two significant figures. This has two significant figures. So our answer can only have two significant figures. We have to round off at this 9, which is in the ones position. We drop that and we get 29 plus or minus 0.5 Newton meters. One more question based on moments. Please do not confuse moments with momentum. Now, the moments of a force of 46 Newton is 56.89 Newton meters. What is the perpendicular distance of the force from the pivot? So we know the force, we know the moment, we want to find the distance. Again, we do have a formula that relates those three things. T is equal to F times perpendicular distance. This time we want to find this perpendicular distance, so we change the subject of the formula. Perpendicular distance is equal to T divided by F. You substitute the numbers you were given, and we get perpendicular distance is equal to 1.2367 meters. Now, if you leave it like that, CSEC will deduct a mark because you have too many significant figures. In this first number here, we only have two significant figures, force, And for moments, we do have 4 significant figures. Remember, for multiplication and division, our answer cannot have more significant figures than the factor with the least number of significant figures. So our answer can only have 2 significant figures. We need to round off at that 2. And so our answer is 1.2 meters. We can leave it like that. 1.2 meters will be acceptable. But just to make sure, we are rounding off at this 1/10 position. Half of the 1/10 position will be 0.05, and we can add that in as our margin of error. Or we could say 1.2 meters, correct 2 significant figures. Before we leave the topic of moments, we also need to learn about the principle of moments. Now, that simply says that if you have a system at equilibrium, the sum of the anticlockwise moments is equal to the sum of the clockwise moments. Mathematically, we could state it as sum of anticlockwise moments is equal to sum of clockwise moments. Let me explain that. Consider that we have an apparatus like this with a retard stand, a ruler balanced on a nail, and we have 2 masses on this side, 2 weights, that one and this one, and on this one we have that one. If the system is at equilibrium, that is, say the ruler is balanced horizontally, then that force times its distance from the pivot plus this force here times its distance from the pivot. If you add those two, you will get the same answer that you will get if you multiply this force here by its distance from the pivot. So the sum of the anticlockwise moments, in this case we have 2 anticlockwise moments, those 2 forces will tend to make that ruler turn in an anticlockwise direction, is equal to the sum, and in this case we only have 1 clockwise moment, that will cause this one to turn in a clockwise direction. So the sum of the anticlockwise moments is equal to the sum of the clockwise moments. Now if we were to add another weight on the right here and adjust it so that it balances, then again, now those 2 anticlockwise moments there will be equal to these 2. The sum of the anticlockwise moments will be equal to the sum of the clockwise moments. Furthermore, it doesn't really matter. We could add a whole bunch, say 5 weights on this side, and we could add 4 on this side. As long as the system is at equilibrium, the sum of the anticlockwise moments will be equal to the sum of the clockwise moments. In this diagram at the right here, the system is at equilibrium. You have this weight at that distance. You have this weight at that distance, and you have this weight, which we don't know, at that distance. We are asked to calculate this weight here. Well, we have 2 anticlockwise moments, this weight times that distance, and this weight times that distance, and we have 1 clockwise moment, which is that weight times this distance. So we will set up our formula that says 8.0 times 0.35 plus P times 0.17, that will be the 2 anticlockwise moments, is equal to 14 times 0.28, that will be the 1 clockwise moments. And so essentially we now have a simple equation here to solve, and we solve and find that P is equal to 6.588. You cannot leave it like that because you have 4 significant figures and all of our numbers here have only 2 significant figures. So you have to round off to 2 significant figures, which would be at this 5, this digit immediately to its right is 8. So we will drop that and increase that 5 to 6. And we get 6.6. We are rounding off at the 1/10th position. Half of that will be 0.05. And so our answer is 6.6 plus or minus 0.05 newtons. Or you could leave it as 6.6 correct to 2 significant figures. Another example, a little harder one. A tapered wooden lamp pole, PQ, is 9 meters long with a narrow end labeled P. It has a mass of 105 kilograms and its center of gravity is 3.5 meters from Q. It is resting horizontally on the ground and the workmen want to lift it vertically by applying a force at end P. What is the minimum force that they need to use? Assume G is equal to 10 meters per second squared. So first, we will draw a sketch to clearly understand what the question is asking. So this is the pole here. That is the pole here. It is tapered, meaning one end is thicker than the other end. The pole is 9 meters long, one significant figure. It has a mass of 105 kilograms. The center of gravity is 3.9 meters from the thicker end. This end here is Q. The workmen are applying a force at F here. We want to know what is the minimum force that the workmen need to apply here in order to lift this pole. Well, if they are applying the force at F, then this end here becomes the pivot. This end is resting on the ground. Now, once we understand that, this becomes a very, very simple question because really you only have 2 forces, one anti-clockwise and one clockwise. So this force here from the pivot is 9 meters because that is the pivot down here. And this force here, right now it's in kilograms. We will multiply by 10 meters per second square to carry it to newtons because weight is equal to mass times gravity. And the distance that this weight is acting from the pivot is 3.9 meters. The working becomes very simple. F times 9 meters is equal to 1050 times 3.9. You solve that and you get 455 newtons out of your calculator. Since the least significant figure we have is this 9, we have to round off to one significant figure, which means we have to round off to the hundreds. 455 to the nearest hundreds will be 500. And since we are rounding off at the hundreds position, then half of that position would be 50 more to 50 less. Or you could just say 500 newtons correct to one significant figure. The next one we are going to look at is Formula 12. Work is equal to force times distance. Work, W is work in joules, F is force in newtons, and D is distance in meters. A construction worker pushed a wheelbarrow 5 meters along a flat driveway using a force of 98 newtons. How much work did he do? Well, we know the distance, we know the force, we want to find work. Do we have a formula relating those variables? Yes. W is equal to F times D. we want to find W, which is already the subject of the formula. So all you need to do is substitute those two, and we get 98 newtons times 5 meters, which would give us 490 joules. We look at the data we are given. This has 1, this has 2, so our answer can only have one significant figure. We have to round off at that 4, which is the hundreds position. So 490, if we round that off to the hundreds position, we get 500. But since we are rounding off at the hundreds position, we take half of that more, which is 50, to half of that less. Normally, when we multiply Newton by meter, we get Newton meter, and we leave it as Newton meter if we are dealing with moments, as in this case here. We multiply force in newtons by distance in meters. We will leave our answer as Newton meters. Now in this case for work, we are multiplying force by distance, so technically our answer should still be Newton meters. CSEC, however, will not accept Newton meters for work, because Newton meters, when applied to work or energy, has a special name, and it is the joule. So you cannot leave this here as Newton meter, saying you're multiplying Newton by meters, and so the answer is Newton meters. No, in the case of work or energy, we have to make sure that that Newton meters is listed as joules. So you could also say 500 joules, correct to one significant. All right, let's look at another example. In carrying a bag of groceries up a stairway, Samantha did 568 joules of work. Assuming that the weight or the force of the bag of groceries was 177.5 newtons, calculate the vertical height of the stairway. In other words, calculate the distance. So we know the work that she did. We know the force that she had to exert to move this bag of groceries. How far did she move it? Well, we know work is equal to force times distance. And so in this case, we need to find the distance. So we change the subject of the formula, make D the subject of the formula, and we get D is equal to W over F. We substitute the data we are given, and we come up with 3.2 exactly. Now, in most cases, you will have more digits here than you require, and you would have to round off. In this case, we have less digits than we need. We only have 2 digits, which means 2 significant figures in this case, but our answer actually required 3 significant figures, since the least number of significant figures in those 2 numbers is 3. So this 3.2, if we leave it like that, we don't have enough significant figures. Normally this doesn't happen. So we add a 0 and we get 3.20. Now we have 3 significant figures. This 0 is the uncertain digit, so our margin of error will be half of that position more to half less, which is 0.005 meter. Or we could have just said 3.20 meter, correct to 3 significant figures. So now we are looking at this formula. Weight is equal to mass times gravity. This W is not work as we did in the previous formula. This W is weight, and it is measured in newtons. M is mass in kilograms. G is gravity, which a good estimate is 9.81 meters per second squared. But sometimes CSEC asks students to use 10 to make it easy for you. A man has a mass of 78 kilograms. Part A, what is his weight on Earth? Assume the acceleration due to gravity is 9.81 meters per second squared. That's part A. And part B of this question is how much less would he weigh on the moon if G, that's gravity on the moon, is 1.6 meters per second squared? So we know the mass of the man, which is 78 kilograms. We know gravity on the earth is 9.81 meters per second squared. What is his weight? We have a formula that says weight is equal to mass times gravity. So we just substitute these numbers that we are given and we come up with 765.18780 newtons. You know you cannot leave the answer like that because this 78 has two significant figures. This 9.81 has three significant figures. Your answer cannot have more significant figures than the factor with the least number of significant figures for multiplication and division. So our answer can only have two significant figures. We will have to round off at that 6. Since this is 5 or more, our answer becomes 770 newtons. Correct to two significant figures. Now his weight on the moon will be 78 newtons times whatever gravity is on the moon. And when we work that out, we get this as his weight on the moon. Well, if that 120 newtons is his weight on the moon, and this 770 is his weight on Earth, how much less does he weigh on the moon? You subtract from that 770, you subtract 120, and you get 650. And remember, we are rounding off at the tens position here, so that we take half of 10, which would give us 5 more to 5 less newtons. There is another way of doing this part B. If you didn't want to go this way, you could have just subtracted the gravity first, so that you subtract from 9.81, you subtract 1.6, and what you get, you then multiply by 78. And that will also give you this same answer here, is difference in weight. The last equation we are looking at in this section is E is equal to mc squared. E stands for energy in joules, m is mass in kilograms, and c is the speed of light in a vacuum. Normally, that is given as 3 times 10 to the 8 meters per second. You don't have to memorize this. This will be given in any question where you have to use the speed of light. So, how much energy will be obtained if 354 grams of matter were totally converted into energy? Assume c, which is the speed of light, is 3 exponent 8 meters per second. So the mass is 354 grams. We said that the mass must be in kilograms. So we need to convert that grams to kilograms by dividing by 1,000. We know what the speed of light is. It is given in the question. We also know that E is equal to mc squared. This equation that is so famous by Albert Einstein that almost everybody knows. We will substitute E is equal to that mass times the speed of light squared. You put that in your calculator and you come up with 3.186 times 10 to the 16 joules. Again, let's look at our significant figures. We have 3 significant figures here. We have 1 here. So our answer can only have 1 significant figure, which is that 3. So we have to round off our answer at this 1's position. And so we get 3 times 10 to the 16th joules, correct to 1 significant figure. Technically, this is not really the 1's position. That is what it looks like in this standard form notation. Next question, relating energy and mass. How much matter needs to be totally converted into energy in order to obtain 6.4 times 10 to the 14 joules of energy? This time, we know the energy, we know the speed of light, we want to find matter. We know E is equal to mc squared. If we change the subject of the formula to make m the subject, then m is equal to E over C squared. We substitute our numbers there. Remember, this is a square. And we come up with 7.11 exponent negative 3 kilogram, which is actually 0.007 kilogram, correct to one significant figure. So we have just completed these 6 formulae. That one, F is equal to ma. Momentum is equal to mass times velocity. Moments is equal to force times perpendicular distance. Work is equal to force times distance. Weight is equal to mass times gravity. And E, energy, is equal mass times the speed of light squared. Now, please note that these simple examples here are just to show how and when such formulae are used. In paper 2, a question may involve the use of more than one of these formulae, a single question. For example, the answer that you get from part A of a question can be used or may be used as the data or the input to part B using a different formula. And this brings us to the end of this video.